so I didn't get up to do last night's, and I'm not going to try it yet. I have been thinking a little bit, and I tried to look at a few hints online that weren't spoilers for Day 22 Part 2. Um, the biggest ones seem to be related to modular arithmetic being part of the clue, and there also seemed to be a clue about trying to write or writing things of the form. Let's see. Let's see. Some form of this. Obviously, what A, X, B, and C were not made entirely clear to me, um, which is the part that makes it interesting. Um, but I think from taking a brief look and doing some thinking last night about deal with increment, I think I could turn each of these into some variation of where X is our input value. I could turn these all into some variation of a constant times our input value plus a constant, all mod num cards. Um, so my first attempt is to just restructure what I have to go for those. And so I'm actually going to like comment out 90% of my code here. And just see whether I'm able to target position. Effectively, I'm just going to see first, can I rewrite these in a way that works as that style of. I'm just gonna stash that up here. I'm gonna turn back on. Deal into new stack. You're just gonna see. Effectively, can I stack twice? Can I represent each of these as the right thing? So for this one, if you're going to take a mod at the end, if I were to take all of this mod num cards, that's fine. So I'm able to take this off because it doesn't matter. So now I am -1 times input plus 1. So I am in the A, which is -1 times X plus -1 mod num cards. And let's see if this gives us the answer it's supposed to. It does. Oh, right. And there's another reason I have to. Another thing I have to tweak here is I need to. Let's see. The .NET implementation of mod will give you out negative numbers, which you generally don't want for what we're trying to do here. So we effectively want an absolute value mod. Let's see here. Public stat. Oh, we have to do value mod. So effectively, we apply the mod normally, then we add the value, and then we apply it again. Effectively, this guarantees that we'll always end up with a positive number instead of ever getting a -1. So, got to put the on here. Okay. 987654321 012345678 9. Okay, so it works for that one. So let's look at the count, or for the cut one. So if we're cutting at a given position, all we're really doing, let's go back and look at cut here. So with a cut, all we're really doing is shifting. We're choosing to start at a different spot, and so all the numbers shift. Which means, so if target position is less than, let's see, I looked at this last night and I had it in my head, and I knew exactly how I was going to do this. I really should have written it down. So target position plus count. I think it's just target position plus count mod. Alright. Because if I want to know where 0 came from, that's target position plus 3 mod. Fine. I want to know where this one comes from. Position plus 3 mod. Okay. So I think it's this mod. This one I'm less confident. Take that out. Okay, so now we got to test out cut. All right, so first we'll do it with -4. So we did cut -4. That's 4 from the end, which means 6 comes to the beginning. 6, 7, 8. That worked. Now, I think the other quirk of, since we're using this mod absolute, I don't think I actually need to do this part anymore. I think it just works. Yep, that worked. Let's just confirm that cut 6 gives the same. Should. 6. 6. Cool. All right, so cut works. Next up is deal with increment. Now this is the hard one, I thought. However, after I thought through this a little bit, I realized, let's see here, deal with increment 3. So all we got to do is effectively, if I want to know what this one is, so 1 minus 3 mod 10. 1 minus 3 is -2. Wraps around to be, oh shoot, that wraps around to be 8. All I was trying to say was that these go down by 3s. So 0 goes to 3. Oh yeah, it's not 1 minus 3. It's -3 times x. So x is 1, so that's -3. -3 mod 10 is 7, and so on. So I think the answer here is -3 times target position. I'll just put this on here for consistency. That. Actually, let's just, again, consistency. So our A here is 1 and our B is count. Here our A is negative, oh, not -3, negative increment. And our B is 0. So let's see what deal with increment looks like now. Seven four one 852 963. Okay. There's one other one to check. This specifically, let's see if we get the same value here that we did for part 1. 750. Not. Oh, that's a shot in the gut. The individual parts worked. Huh. Did I leave something off here? Cards. Cards. Oh, that sucks. Hmm. This 3589 should have given me 2019. Let's just confirm I didn't botch my puzzle input with all those comment, uncomment things. I doubt it, but should make sure. Totally doesn't work. Well, that sucks. Darn it. Now I don't know what to do. I was so prepared to dive in and implement that now. Um Term. Sure, we're not over. Shouldn't be. Not with longs. Might have a chance of doing that. Numbers are. Alright. Huh. Why? I was all set. Like this was my solution. Alright, well, let's figure out which one of these is wrong. Okay, so it's this one that's wrong. Alright, let's step back a little bit then. Let's go back to our two. Oh, no, those are set up properly. Oh, actually, those are not the ones I cared about. It was. Let's look at this. Increment 3. 1, 5, 2, 9. 5, 3. 4. Oh, that doesn't look right. Wait, did I do... Oh, do with increment 3, I didn't actually change the number. Okay. 4s should be 0, and then... Actually, let's just run through this. First I do 0, and 2. I have to do 2 dots, then 3. Oh, it's got a common factor. I can't use 4. Um, 7. The two numbers have to be relatively prime, or the deal with increment isn't even a valid thing to do. After 9, 8, 1, 4, 7. All right. Yep, my algorithm definitely does not work for the 7. All right, I was so proud of that part because that was the hard part. 7. Oh wait, 0, 3, 6. 0, 3, 6, 9. 5, 8, 1, 4, 7. Yeah, that is. I get the same number. Okay. That off to the side then. Then the next ones I ran were do with 7, new stack. Okay. 6, 9, 2, 5, 8, 1, 4, 7. Worked. My other one. Negative 2. 5. No. I'm not in the right spot for this one. Okay. So at least I have a failing case. I checked positive and negative cut already, didn't I? Maybe 9 as well. Doesn't sound right for 9. One should be all the way at the end. Yeah. Should be 0, 9. Interesting. Okay. So let's figure out why this one doesn't succeed. It is not. Why does this work for some of them and not for other ones? This has actually got to be something with num cards here. Could this be num cards minus instead? Sorry, increment minus num. Wait, but then why did 3 work? It's 9, num cards is 10. Work. Why do some of these work then? Keyboard is acting funny. Okay, that gives the right order one for that. Oh, 9 went the right direction. Okay, increment 0 makes no sense. Neither does 1, neither does 2. 3 goes not correctly. Okay, there's got to be some pattern between. Ah, darn it! I thought I had it figured out. 3 goes 0. No, 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 no. It almost just goes. Sometimes it goes forwards and sometimes it goes backwards. The numbers I've computed. And it seems to be related to what num cards mod increment. Or sorry, yeah, num cards mod increment is. That has something to do with it. Okay. So for tens, I can work out what 3 is. Oh, 10's not a very good number. Let's go with 11. 11's prime. It gives start above below 2. Yeah. Go. Generate. Starting with So this one's going to be 0. I'm going to get 6 out the first time. So 7, 1, 2. 2, 9, 10, 11, not enough number. 2, 4, 5, 6, 7, 8, 9, 10, 11. There shouldn't be an 11. Right? That's what the number order should be. Space. Yep. And 3 should be 0. Gonna be first time through I can get out 3 numbers. 4. Second time through. Oh, first time through I can get out 4 numbers, so this will be a 4. Second time through I can also get out 4 numbers. 8. 5. 10. Okay, so the thing is here, notice how the difference between each number is 5. The difference here going the other direction. See, here we go 0, 0, 6, 1, 0, 6, 1, 7, 2. We're only repeating cycles of 2. Effectively, this is a -5. This is a plus. No, it's not -5. It's minus. Yeah, it's -5. This is a +4. So the base 4, we're going to get 3 cycles through the first time. So we get a. We're going to get 3 more cycles, so 6. 10, 2, 5. Okay. And actually, I say -5, but that's actually +6. Right, because 6 plus 6 is 12, which is mod 1 plus 6. 13 mod 1, mod 11 is 2. Okay, so for 5, we're going to get 2 cycles, or 1 and 2 will go in. 0, 2. Oh, no, I'm totally doing this math wrong. No, because these all divide 10. Yeah, I'm absolutely doing this math wrong. The first one was correct. And I should really just have a thing that spits out these patterns. My part 1. I think it's going to be easy once I figure this out, but I believe I have said that before. Uh, this. Gotta search for a target. Just gonna get an output. Okay. Oh, well, that is part of why this number didn't. Okay. So, yep, I could cycle by that. I could cycle by 4s. I could cycle by 3s. I could cycle by 9 because 18 mod 3. I could cycle by 2s. I could cycle by 8, I think. 8, 8, 16, yep. I could cycle by 7, 5, and 10. So the question is how the heck does this number map to that number? Let's try 11 as well. Because I could have a mod involved here. Because if I find, because this number effectively is what my A needs to be. Try this time. Go to, see, 21's not prime. T. I hit debug. Hurry up and run. Two. N. All. 14. 7. Wait a second. Yeah, so if I knew what the second number was, I would be good to go, but I don't know how to find out what the second number is. Oh, of course I do. I know how to find out what the second number is. I have a bad algorithm that gets me the second number. This algorithm gives me what the second number is. Well, Because I'm okay if this is bad. I just need this to not be bad. This would be funny if this works. Not the right number. Oh, right, because I changed this stuff around, didn't I? Just by, yeah. Let's look at the Excel. 06172839410.5. Let's see here. 9, 10, 3, 2716. Okay, that looks good. So now let's disable this. Let's try these two again. Four, 9, 2. Yep, okay, that looks good. Ah, 2019. That is the magic number. Okay. So I'm going to keep this in for the moment. Oop. Because, so now our problem is, fine, so we've computed this. Our problem then is I would still have to compute a really complicated thing. So I think I figured out some other interesting properties of modulus. So what we're basically going to end up doing here is we're going to repeatedly substitute this because we're effectively calling ourselves, right? Or calling a different one of ourselves. So we're going to effectively, and so this would be like, right? So our problem is if we have to, like, so I could effectively build one giant formula, but that formula gets complicated in a hurry. I think I can apply some, whoa. I think I can apply some math here. I think this is equivalent to, I think I can wait and do all the mod at the end. And if that's the case, then I can also do, oh wait, so I can simplify that, or I can turn that into this. Which I can then optimize a little bit if I want by this. Oh yeah, x plus this. Let's see. So effectively that then lets me simplify this part and this part, keep the numbers from getting too big. And then I'm effectively left back with a function in that format. Now, what I don't know for a fact is whether you're actually allowed to do that or not. I'm just kind of guessing. Well, sorry, I'm not guessing. I'm doing a little more guessing, but not a whole lot more. Again, version of this. Now we're going to start playing with the big numbers. But my theory is that. So if I have so I'm going to take a thing that takes in A and B and then has a public math. I'm going to take one, I'm going to apply the other. So my outer one, the one I'm, or so this is the D and E here, but effectively, so let me just, how to trigger. Okay. So by my math here, oh, whoops, I also need C. Okay. So all I have to do then is say A time. Okay, so since we're the input, we are D. Absolutes. C. Wrap.c. Okay. And we are A. Sorry, it's the other. Which is our constant. Wrapper's constant. C. And we'll still have the same C that we had before. So what I'm hopeful of is I'm basically going to have each of these returned on Math Evaluator. Cards. This one. Count cards. Harder one. Don't have to take this. Now, down here we did A and start out with the result of effectively the identity on math evaluator. Say okay. Easy peasy. Somehow I don't imagine it's going to be that easy. But hey, well, we could try, right? Let's apply position. Okay, so now we see if any of our math still works. Let's start with the simplest things. Build new stacks. This one's easy to verify. Yep. Yep. Okay. Which actually means, well, that doesn't actually mean we're doing our order of evaluations correct, but we can do that. Okay. Let's check our deal with increment is working correctly. Top spreadsheet 0612 is good. Oh, did I see some? I thought I saw some negative numbers in there. And 010, yep. Okay, so that looks good. Check our cuts. 6655. Good. Okay, so now for the part that's probably not going to work. Because in order for these to work, I would have to be properly merging things together. So 369258147. Nice. Nice. Okay. That appears to work. Right. That appears to work too. Woo. Okay. Modular math. So now what I've got here is, okay, compute. Actually, let's just oh, yes, I forgot the other part. Simplify. Oh no, I'm already simplifying as I go. Never mind. Cool. Okay. So effectively, that's the formula that it spits out for a single application of this. So let's disable this one now. Now we'll run the hard one. So this is the formula this spits out. Now what's going to be interesting here is I want to compare this to the formula that I derived with Excel the other night. Here we go. I mean, other than the mod parts, that's the times. Yeah, that's not even close to the right number. However, that number does look shockingly familiar. Fortunately, I don't copy down. All right, but anyway, so I now have a function that will relatively trivially compute how long it takes, or sorry, what the source of a single shuffle looks like. Okay. So now comes the really, truly clever part. I'm going to tell it. This is the part that, well, we'll see. So we're going to start out with compute being a single shuffle. Um, okay, so if we want effectively what I'm going to, well, here, we'll see if this all works out or if this explodes in my face. Put to compute. So, because I could just call. So if I call compute as input to compute, now we'll have a function that can do 2 shuffles. Well, if I then call it again, I will have a function that can do 4 shuffles. And I call it again, I'll have a function that can do 8 shuffles, and so on, and so on, and so on. So my thought is, I'm just going to, as I'm building up my power of 2 shuffle thingamajiggy, I will apply it if the bit that this would so effectively this will tell me, do I need to apply, so effectively if the number is odd, this will trigger the first time through, and then I will equal that. Target position, compute, apply. Let's see, I have to make this. Actually, I might not even need, because of this approach, I might not even need this to be big integer, but it'll probably be easier if it is. Okay, cool. Okay, do you shuffle that many times? So I did something wrong. Shuffles. Shuffles computes. Oh, 1. Not equals 0. This should be long. Alright. This works. It's not going to. Holy crap, that is the right answer, and I did not have to use matrices. One of my former coworkers who I've been chatting with about this problem for the last day or so um, said from what he looked at, you needed matrices to solve this. I solved it without matrices, and I solved it without looping a billion or, hundreds of trillions of times. So the trick here was, well, okay, first trick was to realize that you needed to solve backwards. Turn. So we know we need the card at a specific position. So instead of trying to simulate all of the cards and all the shuffles, we just say, okay, well, I need to know this one. Where did this card come from? So these functions here, deal new stack, cut, deal with increment. These functions build this mod math evaluator, effectively they build a way to know where the original card comes from in this form of a times x plus b mod c. And then we take advantage of the fact that, so I build that up for each one of these. And then I take advantage of the fact that you effectively mod, at least under addition and multiplication, modulus operators are you can shove them around pretty much wherever you want. So I can refactor. So like after I place one into the other, I can rework this so that I can pull the mod out of here. I can merge several of the numbers together, and then I can then redistribute the mod back out across these to simplify them. That's why you saw, even as I get up to giant numbers, I'm really not dealing with that big of numbers in my, like this is the A, B, C of that formula. Um, and then I work my way up, and then I take advantage of the fact that if I call compute dot apply, or no, where is it? Compute dot as input to compute. That's effectively I take my current compute and I nest it inside of another instance of itself. And effectively, if compute can currently shuffle once, compute as input to compute will shuffle twice. If compute shuffles twice, compute dot as input to compute will now shuffle 4 times, and so on. And you repeat that long enough, and eventually you start like, okay, well, if compute can shuffle 167 million times, then compute dot as input to compute will now be able to shuffle 335 million times, and so on and so on. Effectively, every time I go through this loop, I am doubling the number of shuffles that this compute function represents. Well, it's not actually a function, but it kind of is. Um, and so as I work my way up it, I mean, I could have just kept track of what the right ones were that I needed and then merged them together at the end, but I'm just applying it as I go. I effectively say, hey, I'm knowing that I'm going to get every power of 2 showing up here. Like, if you know your powers of 2, 1, 2, 4, 8, 16, so on. I know I'm going to get every power of 2 show up in here at some point. So I'm just going to say, well, knowing that, because you could also work from the higher down, you just apply every one of these where the num shuffles is greater than it. You apply the biggest one. Sorry, you had them all to begin with. You could just say, uh, um, uh, give me the largest number of shuffles that I have a function for that is smaller than num shuffles, and then apply it, and then repeat. And you'd effectively do the same thing. You just be doing it in reverse. I just did it while I'm building it. But effectively, I'm assembling a function that can shuffle a ginormous amount of times. Yeah, I managed to turn a. I effectively made my final calculation complexity log n, right? As in, I have to calculate this many times. I take log of that divided by 2. 46 times. Effectively log base 2. Yeah, that's somewhere about 46. Yep. All right. I feel better now. So the only math trick required here was realizing that if we could express each of these as a times x plus b all mod c, that there would be other value to it. That is one part I got from Reddit. Was somebody was suggesting that. Now, no one explained to me why I wanted them to look like this, or at least the thread I was looking at. Threads I was looking at. No one explained why I wanted them to look like this, or how I was supposed to get them to look like this, which was the infuriating part. But I managed to get there eventually. Although this one required this this really this really like not so amazing implementation my old one, but it got me the key value I need. And the key part here is this code here only runs when I'm doing the parse part at the beginning. Once I kick out a ModMath evaluator to do all the actual work, golden. And because the ModMath evaluators combine so seamlessly, yeah, this actually worked. Yeah, do I know how far? We'll see if I can tell how long I've been streaming. Oh, there we go. It says right there. It says I've been live for about an hour. So this only took me about an hour to put together. Now, granted, that's after a bunch of theorizing over the last couple of days. Namely, when I'm about ready to fall asleep, my brain can really not shut off with this. When I have a problem like this, was it there? Oh, there's an XKCD for this. There's an XKCD for everything. Sniping. Yeah. Yes, when you're presented with a interesting problem, it's very hard to not try to solve it. So, all right, I don't think I'll stay up for day 24 tonight, but I probably will pop back on a little while later and take a stab at day 23. I think somebody told me, or a former coworker who has been trying to compete with me on this, but he's not getting up at midnight, so I'm getting ahead most days. But he said it was relatively easy. Oh yeah, Gold Star closed at 20, Silver Star closed at 11. So okay, so I shouldn't have to plan for more than 45 minutes or so. All right. Well, I just committed it and my code is pushed up. So yep, it's on GitHub if you want to take a closer look at it. For some reason, all 0 of you who are actually watching this stream. Yeah, I did. So I did have to get this hint. But I'm pretty proud that I managed to make the rest of it work without having more hints. And it sounded like some of the other discussions that I was trying to follow that were trying to give me hints were totally not making sense. They kept pointing me to this thing called modular arithmetic, which I don't think, from what I looked at, I was not seeing anything that was giving me this stuff. If I would have seen this stuff, then maybe it would have clicked why I needed this. Um, I don't know, or maybe I read it and it didn't sink in until I tried to fall asleep. But anyway, I got to solve. I have to steal somebody else's code. I did have to get some hints, but there, there was also a thread somebody posted on the Reddit for Advent of Code, complaining that this was too mathy of a problem. And I kind of do agree. Like, this required some clever math tricks that is not normally associated with programming, but then somebody else did point out that this kind of clever math, something about modulus arithmetic, is a common thing in, they didn't talk about this or this specifically, but modular arithmetic being a common thing to deal with in cryptography, which I would guess I wouldn't know. The only cryptography code I've ever written is like using MD5. Like, I just import a library. Um, yeah, I'm well in the thing of the, if you don't know what you're doing, you really shouldn't write cryptography. So I don't write cryptography. Anyway, yeah, a little over an hour. Got it to work. Did get sidelined with this whole getting deal with increment to work right, but once I got that, like, this mod math evaluator thing really did work the way I was expecting it to. So cool. That's nice. I don't like having this thing over my head of this thing I didn't get implemented. So signing off for now, but I may be back on later to do the 23rd, and then I'll probably be on tomorrow evening to do 24th. And since I am not going to see family over Christmas, I may actually be on for doing the night of the 24th. Plus, now I'll have all, hopefully, 48 stars going into the night, so I can try to pick up a few extra points, getting the first star quick, and then picking up the second star for having all 50. With that, I'm going to sign off for now. Good night.